This talk is a slightly modified version of one presented at the Informa Decarbonising Rail Conference in Sydney in August 2004. Rail emits only 1% of Australia's CO2. Our cities are electrified, but outside the cities, diesel powers both passenger and freight rail. Western Australia's share is 51%, and this is nearly all from Pilbara iron ore. There are around 2,200 locomotives and 250 diesel multiple units in Australia, most of which would still be in service in 20 years' time if it were not for the 2050 net zero target. Also, the safeguard mechanism requires a 4.9% per year reduction until 2030. There is no easy way to achieve this. Only 3,400 kilometres out of about 40,000 kilometres of track is electrified. And at around $5 million a kilometre, it would cost around $183 billion to electrify it all. Batteries and hydrogen are proposed as a cheaper way to net zero emissions. Batteries will allow journeys of 200 to maybe 500 kilometres, which fits the Pilbara, where all the miners are planning to go for batteries. But for the longer journeys, hydrogen is proposed as the best solution. Whichever technology is used, conversion of 2,500 locos and DMUs would cost at least $12.5 billion at $5 million each, with 100 a year until 2050. But imagine if there was a zero-emission drop-in replacement fuel which we could use in our existing locos. Unfortunately, it isn't biofuel, which is only sustainable when made from used frying oil, and there is not enough of that to go around. Rail consumes about 1,500 million litres of diesel annually, which would require 4 million tonnes of grain. That is about double our total canola harvest. The trains pictured haul grain to feed the world, and displacing food production for fuel would not be acceptable. But what about synthetic fuels made from inedible biomass? Dimethyl ether can be made from methanol. With heat, pressure and a catalyst, two molecules of methanol join to give one of dimethyl ether and one of water. DME has a high cetane rating and can be used in a diesel engine, unlike methanol, ethanol, methane or ammonia, which require a pilot fuel to ignite them. It produces almost no soot, as it has no carbon-carbon bond, and for this reason was trialled in diesel buses in the late 1990s as a way to reduce urban pollution. NOx is also lower than for diesel. But there is some downside. It is similar to LPG and is a gas at room temperature. However, it can be liquefied at moderate pressure, 500 kilopascals at 20 degrees C, a pressure which rail is used to working with in air brakes. It is a fuel like you use for a barbecue as opposed to rocket fuel. To be useful, hydrogen must be compressed to 70 megapascals or liquefied at 20 degrees above absolute zero. Another downside is that its low viscosity makes it a poor lubricant, increasing wear on injectors. And the last point, it does have a lower energy density than diesel. But is it really net zero? CO2 is released when you burn DME or any synthetic fuel. But putting this into perspective, it is estimated 830 million tonnes of CO2 was released in the terrible bushfires at the end of 2019. But we don't count burning wood when there is regrowth. Australia's official CO2 emissions for that year were 528 million tonnes. Methanol can be made from wood or any biomass. The first step in making methanol is heating biomass without combustion to produce syngas. This is a mixture of carbon monoxide, hydrogen, carbon dioxide and some methane. Making methanol requires a 2-to-1 ratio of hydrogen to carbon monoxide, and syngas typically has less hydrogen than carbon monoxide. It is therefore necessary to increase the hydrogen proportion using the gas-water shift reaction, which unfortunately creates more carbon dioxide. This could be avoided if you had a source of renewable hydrogen. But without renewable hydrogen, about 8.5 million tonnes of biomass would be required to make the DME equivalent of 1,500 million litres of diesel. This is not outlandish. Australia exports around 12 million tonnes of wood chips annually. However, if aviation and road transport take the synthetic fuel route, there'll be competition for biomass, and they need a lot more. Australia has some very long rail journeys. For example, Adelaide to Perth is 2,655 kilometres. Trains must refuel at Cook in the middle of the Nullarbor, and another train must take the fuel there, or use in-train refuelling like this SCT train. Note the two tanks on the wagon behind the locos. These continuously top up the loco tanks. Fuel used for this 6,000 tonne train is about 36,000 litres, which the locos convert into 150 megawatt hours of electrical energy. No one is suggesting using batteries for this, but if you used battery electric tenders, as Horizon is considering for medium distances, 150 megawatt hours would require 22 of them. They would take up 29% of the payload, although on the positive side, energy costs would be less than half the price of diesel. For longer hauls, Horizon are considering hydrogen electric tenders. As in the picture, these will include a tank of liquid hydrogen, the fuel cells, and all supporting equipment. So from the loco side, it looks like a large battery. 7 of these would be required to provide 150 megawatt hours. This is still 9% of the payload and would need a lot of cabling. Or if supplying hydrogen through hoses is acceptable, you could put the fuel cells, etc. in the locos, with a separate tanker in between, in an arrangement like that used by Florida East Coast with LNG in the USA. Their diesels are modified to burn up to 80% methane. The LNG is gasified before being transferred through hoses to the locos, as this is less hazardous than trying to transfer a cryogenic liquid, and liquid hydrogen is 90 degrees colder. With this configuration, 11.8 tonnes of liquid hydrogen would be required, and would be at least 3 times the cost of diesel. Like LNG, the liquid hydrogen would have to be stored in a tank with an inner and an outer shell with an evacuated or insulated space in between. Space constraints mean 2 tankers are needed for 166 cubic metres, which is not in itself objectionable. However, you need to fill the tanks, and the supply chain for liquid hydrogen requires very specialised equipment. There is currently a trial in Victoria called the Hydrogen Energy Supply Chain. Hydrogen is made via syngas from brown coal in the Latrobe Valley and trucked to the port of Hastings, where there is a plant to liquefy hydrogen. It is then taken to Japan in the world's first ship built to carry bulk hydrogen. The 8,000 tonne ship carries 1,250 cubic metres of hydrogen, but this is only 90 tonnes. Barely enough for 8 trains to Perth. This supply chain can only function with massive subsidies and illustrates the barriers faced by an early mover. Toyota and Hyundai began planning fuel cell powered cars long before Tesla appeared on the scene, but EVs can now match the range of fuel cell cars for less than half the price. There are very few filling stations outside of California, and even there, Shell has pulled out of the market. Nobody is buying fuel cell cars. Nikola and others are still developing fuel cell trucks. If they find customers and a supply network is rolled out for trucks, rail could follow. The truck fleet consumes 5 times more diesel than rail. But if battery-powered trucks, which can provide the range, seize the market, there'll be few customers for green hydrogen, and it will remain rare and expensive. Which illustrates that dimethyl ether would be a much easier solution. You would need 72,000 litres to get to Perth, about twice the volume as for diesel, but a volume which can be accommodated in a tank only slightly longer than this LPG tanker which Comenge built in the 1970s. The cost of dimethyl ether would be perhaps 50% more than diesel. Just as for hydrogen, a supply chain for dimethyl ether would need to be established. 1.3 million tonnes of methanol per year would be needed to make fuel for half the existing diesel fleet, assuming the other half goes for batteries. Australia's only methanol plant closed in 2016, and we now import all our methanol. However, Able Energy has plans to build a plant at Bell Bay in Tasmania to make green methanol for shipping. They are currently raising capital and hope to be producing 300,000 tonnes a year by 2028. 4 or 5 such plants around Australia would satisfy the rail industry. In total, 4 million tonnes a year of biomass would be needed, which is 11,000 tonnes per day. As a quantity, that is only slightly more than one train of coal in the Hunter Valley. But typically, trains hauling wood chips are more like this one running to Albany. We would need the equivalent of 3 of these per day serving 5 methanol plants around the country. Now you might be thinking, in view of the bother of DME being a gas and requiring pressure vessels for storage as well as engine modifications, would we be better off making synthetic diesel using the Fischer-Tropsch process? Unlike biodiesel, which is an ester made from fatty acids, synthetic diesel has the same properties and chemical composition as petroleum diesel oil. It burns exactly like diesel, with no engine modifications required. The Fischer-Tropsch process was invented in the 1920s and can produce any hydrocarbon from biomass, although more usually from coal, as was the case in South Africa and wartime Germany. I don't have any numbers to back this up, but I believe Fischer-Tropsch would be more expensive. Also, having a much higher ratio of carbon to hydrogen, direct CO2 emissions would be higher than with DME. In conclusion, the pros for DME are that it can be used in existing locomotives with some modifications. It is carbon neutral if made from biomass, and it is cheaper and much easier to store, transport and handle than liquid or compressed hydrogen. I suggest it could be a viable path for the Australian rail industry. Rail demand is sufficient for an independent DME ecosystem, while hydrogen requires economy-wide changes. The DME economy requires methanol production, sources of biomass, and rail links to the production facilities. If put in place by the early 2030s, it could carry us through to the mid-2040s, by which time better technologies may have emerged. This could be a concrete plan to present to government, and if successful, many other countries would be interested. So, don't send your diesel to the scrapyard just yet.